Hey folks, sorry I couldn't be here today. Um, we will make do with a little video. Hopefully this is not entirely painful. It's kind of like last year when COVID made us go online. What we're going to chat about today, what you're going to learn about today, is what we were playing with yesterday with our paper towels. We are going to look at water. Good old H2O. It's a really important molecule in biology, so we are going to spend some time learning about it today. If at any time you need the TOC to pause the video, just ask. I don't know if this will be easy to follow or not, as in real time if you're writing notes down. So if you need to pause it, feel free to do so. If you have any questions, ask away or hang on to them. I should be back tomorrow, I hope, and we can do a quick review, so no big deal. So chatting about water makes up about 60 to 70% of the mass in our body. So we are mainly water, which is kind of weird. Even though we're people and we're all very different, we're basically made out of the same stuff, which is just H2O, which is coming out of the tap. So in terms of water and its structure, it is a nonmetal joined to a nonmetal. Chemists in the room, what kind of bond is that? A nonmetal joined to a nonmetal. Oh, very good. I can hear everybody shouting out the answer. I know that you know that we are talking about a covalent bond. It's a covalent bond, which means water is a covalent compound. And remember, in a covalent compound, that means that the water molecule itself is sharing electrons. And I'm just going to put E- for electrons if that's okay. Now, what's kind of cool about water itself is when it shares electrons, it does that, but it shares them unevenly. So if we look at the structure of a water molecule, you've got an oxygen that ends up with a couple of hydrogens that are sharing electrons with it. But this big negative oxygen is kind of hoarding the electrons a little bit. It's pulling them a little bit tighter than the hydrogens can. So what we end up with is the oxygen in this case having a partially negative charge. So that's the little symbol for partially. So that end of the water molecule is going to be partially negative. That oxygen would even have a couple of extra little free pairs of electrons there. So it's pulling the electrons more strongly, so that end of the water molecule is negative. The other end with the hydrogens is not pulling those electrons as strongly, so it's got a partial positive charge. Again, crazy little symbol for partially. So partially positive. Overall, the molecule is neutral. Oxygen is -2 and each of these hydrogens is +1, so it balances out. But we've got this negative region in the oxygen end and a positive region at the hydrogen end. And what we call that is we call it a polar molecule. And that's really important for water. We're going to chat about a bunch of different important biological characteristics of water. And it's all because water is polar. So polar means it has a positive end, it has a negative end. Again, we had said partially positive, partially negative, but overall the thing is neutral. So it's unevenly sharing those electrons. Partially positive, partially negative, they balance out. But that partially positive and partially negative end, sorry, there's the word, I'm chatting too much here, is going to make the thing polar, which actually kind of makes it like a mini magnet, to be honest. You've got a positive, slightly positive end here with the hydrogens that can attract other things that are maybe slightly negative. And then you've got this slightly negative end with the oxygen that can attract things that are slightly positive. Random Jeopardy fact. Everybody loves Jeopardy. The next time you're on it, you don't have to memorize this number, but this is kind of sort of the sketch that I've done here of the water, is a lot like it actually is. There it is, tongue twisted. The angle between the two hydrogens, just because you're curious, right? You're going, well, what the heck is the angle? It looks like the hydrogens are on one end. They are. And they're 104.5 degrees apart. So you think about this thing being 360 degrees around, these two hydrogens are much closer to each other. It doesn't just make a straight line. Water doesn't just look like this. That would be 180 degrees between the hydrogens, so that's actually not what happens. Anyway, you'd never have to give me that number, but if you're ever on Jeopardy, the next time you're on Jeopardy, now you know. So you're a bunch of critical thinkers, and you might be sitting there in your seat thinking to yourself, well, if water, a single water molecule has this slightly negative region towards the oxygen and a slightly positive region towards the hydrogens, then wouldn't that make it bond with itself really nicely? Because if we brought another water molecule close to this one, maybe I'll go down to the next page and resketch it. Wouldn't that mean that this slightly negative end would maybe attract the slightly positive end on another water molecule? Like maybe one of the hydrogens? You could end up with this kind of thing. And then on the flip side, there'd be some attraction there. On the flip side, couldn't one of these positive hydrogens attract a slightly negative oxygen on another water molecule? And kind of have an attraction like that? And the answer is yes, indeed. This is how water bonds to other water molecules, is the slightly positive hydrogens bond to the slightly negative oxygens and vice versa. You can imagine there would be stuff happening like this all over the place. Those bonds that form between, maybe I'll do them in a different color. So these red lines I'm drawing that represent the bonding or the attraction between the slightly positive hydrogen end and the slightly negative oxygen end, those are called hydrogen bonds. So individual water molecules are attracted to each other. This should probably work in real time, hey? If I'm writing it down, I'll bet you have time to write it down as well. They're attracted to each other, and they're attracted to each other with hydrogen bonds. So that's the specific kind of bond between the hydrogens and the oxygens. We call them hydrogen bonds. For short, you'll see me if I refer to them again in this presentation and write them down, we'll just call them H bonds. Short for hydrogen. Save our hands. Now, what's really cool about these hydrogen bonds is that they're actually incredibly strong. Relative to a lot of other attractive bonds that join molecules together, these hydrogen bonds have a lot of strength, and it takes a lot of energy to break those hydrogen bonds. One of the things you probably know that these hydrogen bonds are strong, because I'm going to imagine that everybody has experienced something like a belly flop. And that belly flop, the reason why water hurts when you hit its surface, is because all those water molecules are stuck to each other with these hydrogen bonds. And again, I can assume that we've probably all experienced those hydrogen bonds. It takes energy to break them. You smack that water. It doesn't always feel very good. So we get this sort of mesh-like structure that's formed. with all these hydrogen bonds. So that's the general structure of water, single molecules and how they sort of join up on them or attract to each other. So now if we look at sort of features of water, so based on it being polar and being attracted to each other and bonding with these hydrogen bonds, what are some other specific characteristics of water that are useful for us as living organisms? So we could have called that maybe structure to start. You could add that in if you want. Sorry for doing that after the fact. And based on that structure, we can get into properties of water. Maybe let's call it that. So what are some of the specific properties that we need to know in a Biology 12 class? We're looking at sort of how this impacts life, specifically for people, but I will throw some other examples in there too. So two really important properties that are linked to the polar nature and hydrogen bonding nature of water is these two terms, which I bet you've heard before, and you might know the difference, or maybe you know one of the two, but you might know the difference between the two of them: cohesion and adhesion. And I think it's maybe the adhesion that you may have heard of before. Things that are adhesive means they're sticky. So adhesion is when water sticks, and I'll put that in sort of quotation marks, when it's attracted to, when it sticks to other substances or surfaces. And I think everybody can sort of picture water in some scenario and go, oh yeah, I know water sticks to things. Because what do you notice is true of the shower door when you're done showering? There's droplets of water stuck to it. And that's a vertical door with the force of gravity pulling down on all those water droplets. And yet the attraction between those water molecules and the glass or the fiberglass shower, it doesn't really matter what the surface is. That attractive force is greater than the force of gravity, which is quite impressive. So water sticks to other substances or surfaces, whether they're horizontal, vertical, it doesn't really matter. Cohesion is quite similar, but it's not when water sticks to other substances, things that are cohesive, That's when, here we're talking about water specifically, when water bonds to other water molecules, when water sticks to itself. So when H2O bonds to other H2O molecules. So it's sticky on itself. It's like Velcro sticking to other Velcro, as opposed to Velcro sticking to your sweater. Velcro sticking to your sweater, maybe we could use that analogy saying, oh, it's adhesive, it sticks to other stuff. And then Velcro sticking to more Velcro, hey, that's the cohesion. Two things that are alike sticking together. So when H2O bonds to other H2O molecules, we call that the cohesive nature of water. Now, how is that important for living organisms? So we're talking about humans specifically in this course, but I actually am going to switch gears to another living organism that's not a person. We're going to think about a tree. So trees, some of them really tall. Like they can be hundreds of feet tall. And what needs to happen in a tree is water, which the tree is getting from the ground in its roots, needs to somehow make it hundreds of feet into the air against the force of gravity to get to the leaves or the needles in the canopy of the tree. So how the heck does water move up that tree? How does H2O move from the roots to the leaves. Well, it turns out it is both cohesion and adhesion that allows water to make that trip hundreds of feet vertically against the force of gravity. So I guess what we have to go to is maybe what's happening in the leaves, and you might know this, hopefully you know this. So H2O that's in the leaves or needles, I'll just put leaves for now. When water is in those leaves, it's going to evaporate. So that means it's moving out of the leaf and it's floating into the sky. So there's your leaf. Now, as that water evaporates, it is stuck. It is cohesive. So it's stuck to other water molecules. So when that water in leaves evaporates, the cohesion of water pulls other water molecules upwards, because as those water molecules are evaporating into the sky, they're pulling all of their other friends upwards with them, right? It's like a chain. It's like somebody pulling on the top of the chain at the leaves, and that's going to pull the other, going to pull all the other links of the chain up with it. So the cohesive nature of water allows that water to move upwards against the force of gravity. Cohesion of H2O pulls other, maybe I'll say joined water molecules, because they're joined with those hydrogen bonds. Joined molecules upwards. And then also what's happening is there's adhesion. So the adhesive nature causes the water to stick, again in air quotes, it's just an attraction, but it causes the water molecules to stick to the, I'm going to throw a name out here. If you remember it, that would be awesome. If you don't, it's not a huge deal. It sticks to the xylem cells. Xylem is the sort of water pipework in a tree. So it sticks to the xylem cells, and that again counteracts gravity. So water getting pulled up by other water molecules, and then water adhering, sticking into the sides of these xylem cells. And again, the xylem cells, just to put that in brackets, this is like the water pipes of the tree. So cohesion and adhesion working together to move water from the ground, from the roots, all the way up to the very top of a tree. Pretty darn cool. All right, so we've got those two properties down. They're kind of almost the same, right? Very, very similar. Moving on to, I guess, the second property. I'll call that maybe the first one. The second property is that water is considered the universal solvent. So it's a very, very good solvent. Maybe I'll go label this 1. We'll label this number 2. So water is a very good solvent. And chemists in the room might know this. If you're not a chemist and you don't know what a solvent is, that's okay, I'm going to tell you. A solvent means that it's a substance that can dissolve other things. So solvent dissolves other substances. One solvent that I like to use around my house, I actually just used it on the weekend, is a solvent called Goo Gone. And if you've ever used it, it's this awesome lemon-smelling liquid that is a really good solvent. That means it dissolves things really well. And Goo Gone specifically, I use it for removing sticker residue. Because I told you, I think yesterday, that I've got kids that are 8 and 10 years old, which means they love stickers. And stickers end up all over my house. And my daughter especially loves to buy stickers at the dollar store, cheap, crummy stickers that she puts on things, even though I ask her not to. It's okay, I love her to bits. And then when I go to peel those stickers off, they leave horrendous sticker residue on whatever surface they're on. And you probably know, if you've had experience, that getting sticker residue off of substances or surfaces sucks. It's not an easy job. So that's when I go to the Goo-Gone, which is a really good solvent for specifically dissolving sticker residue or tape residue. So water does some really good dissolving, not necessarily of sticker residue, but just in terms of being more useful in terms of life. Because water is polar and because of its hydrogen bonds, it is very good at dissolving other polar molecules or other polar substances, throw whatever term you want to put in there. Maybe I'll say substances. So other polar substances, and it's really good at dissolving ionic substances, ionic compounds. Chemists in the room. Ionic compounds, what are they again? Oh, maybe you're not shouting it out loud, but an ionic compound is a metal joined with a non-metal. Really, really good example of ionic compounds, salt, NaCl. And you know that water's really good at dissolving salt because I'm sure you've used saline solution at some point, right? Gargling it, or what else would you, eye drops or saline substances. IVs are often saline substances. So you put salt in water and it dissolves really nicely because water's a really good solvent. So here's what's kind of cool. When you put something like salt, table salt would be NaCl, sodium chloride. When you put it in water, it actually is going to disassociate. It separates into positive sodium and negative chlorine ions. So it separates into these ions. Water is actually going to disrupt the attraction between the NaCl's and kind of take over and split them apart, which is really, really cool. But then what I think is the neatest part is that when you have the Na and the Cl split apart, think about what the water molecules might do with this positive sodium. Remember, water is polar, which means it's got that partially negative oxygen end. And what the water is going to do is this Na is all positively charged. It's going to get surrounded by partially negative oxygens that are part of water molecules. So I'm going to draw 5 of them surrounding this sodium. It turns out there would probably be hundreds, if not thousands, of H2O molecules surrounding this Na plus ion. But I don't have the time or desire to draw all those, and you probably don't either. But we have this water surrounding, again, partially negative, partially negative, partially negative, partially negative, partially negative, attracted to the positive. We have this surrounding of the sodium by the water molecules. And then let's switch gears. You can probably predict what's going to happen. What about the chloride ions? Well, they're partially negative, which means water's going to be attracted because there's a whole bunch of partially positive hydrogen ends. So you're going to have a whole bunch of the partially positive hydrogen ends of water molecules attracted to the chlorine, and it forms a little circle around it, just like we did with the positive NAs and the negative O's. Sorry, I'm just going to draw 4 because it fits in there nicely. But you end up with these sort of circles of water molecules that surround these charged ions. And these circles of water molecules that surround them are called hydration shells. Kind of like an eggshell, but it's made out of water, so we call it a hydration shell. So hydration shells. So H2O surrounds charged ions. And it doesn't have to be NAs and CLs. That's just an example I've used because that's table salt. That's a really common one. It could be any ionic or any charged particle. So that's kind of a neat feature of water. That's what helps it dissolve things really nicely. Number 3. We actually chat about this property of water. There's the word I'm looking for. In physics. Water is a really good temperature buffer. When things are buffers, that means they resist changes. So water as a temperature buffer means that it's actually very resistant to temperature changes. So in physics, we talk about a feature of water called its heat capacity, or its specific heat. Maybe I'll go with that, because if anybody's taken physics, you'll remember this. So specific heat of molecules tells you how much energy it takes to heat them up. It's the amount of energy to heat up that substance. To heat up, maybe I'll just say a material. And actually, I'm going to pause the video here. I'm going to grab a chart for you and show you how the specific heat of water compares to the specific heat of some other substances that you've heard of before. All right, hopefully you can see this. Here's a table we use in Physics 11 and 12, specific heat of common substances. So these are how many joules, how much energy it takes to heat up these different materials. It's actually how much energy it takes to heat up 1 kilogram of the material by 1 Kelvin, which is the same as 1 degree Celsius. So if you have 1 kilogram of aluminum, it would take 903 joules worth of energy to heat up that 1 kilogram of aluminum by 1 degree Celsius. So if you scan those numbers, you know, they're all in the hundreds, and then you get ice, which is a type of water, over 2,000. You get methanol, which is going to be a lot of water, over 2,000. And then you get to water and you go, holy smokes. Water has the biggest specific heat by far of any other substance. And what that means is it absorbs a ton of energy before it's going to change temperature. So again, look at it compared to these other things. It's actually a really good thing for humans that we're full of water, because that maintains our internal body temperatures at a very consistent level. If we were made of something like Silver Surfer, for all the Marvel fans out there, then we would actually heat up like really quickly, which could get really dangerous. Our body doesn't like to be too warm or too cold. It likes to just be in homeostasis, kind of a happy medium. So water specific heat is equal to 4,180, which is huge, the biggest. And that means it's really resistant to temperature change. It will change temperature, but you have to dump a huge amount of energy into it to have it change temperature. And again, why is that a really good thing for us? Well, it's a really good thing because it keeps our bodies at a relatively consistent temperature. And again, that internal temperature that your body's trying to keep is somewhere like 37, 38 degrees Celsius. So 37 to 38 degrees Celsius. And you can get too cold. Sometimes our body Sometimes that water loses too much energy and it cools down. You can end up in hypothermia. Or sometimes you can actually get too hot. Like you're outside exercising aggressively in the sun, or you're fighting off a pathogen. Your immune system will warm your body up, and that is hyperthermia, when you're too warm. I will show you, or the TOC will hopefully be able to show you a couple videos on temperature buffering for humans, and also there's a really cool one for kangaroos. But that's a really good thing. That consistent temperature we like to keep. Our body likes to keep a lot of things consistent. And you maybe have heard this term. I might as well introduce it for the first time right now. Our body is trying to stay in homeostasis. It's trying to keep the internal conditions. There's lots of stuff. Temperature, pH, water balance, blood pressure. There's tons and tons of things that our body works really hard to keep steady for the most part. And that is the body's desire for homeostasis. So water helps with the temperature piece for homeostasis. So really, really important, really, really thankful, useful that we are 60 to 70% water. Now, related to temperature buffer, I'm going to throw one more property in there. We're almost done the lesson. You've almost made it. Thanks for hanging in there. So temperature buffer. And number 4, sort of closely related to temperature buffering, is evaporative cooling. And you probably know that our body, when we're working towards hyperthermia, when we're starting to get too hot, one of the first ways that our body counteracts that to try to get back to homeostasis is sweating. And sweating is an example of evaporative cooling. So evaporative cooling is when water on a warm surface or hot surface, put in whichever word you want, water on a warm or hot surface evaporates. We know that. The hotter the surface, the more likely that water is to evaporate. And what's really cool is when water on a warm or hot surface evaporates, it removes with it, it pulls away, it removes energy during this phase change. So hopefully you've talked about water in its different phases, like solid, liquid, gas, or vapor. When water goes on a hot surface from liquid phase to gas phase, it's going to suck away a whole bunch of energy, steal a whole bunch of energy with it. It removes energy during the liquid to gas phase change. And that's a really good thing when we're starting to get hot, because when that water leaves, it's taking away that heat energy, which is leaving us cooler. Now, remember, it needs to do this a lot because water is really resistant to temperature changes. So it takes a lot of sweating to cool down your body if you're starting to get really warm. I am generally a cold person, but when I go for a run, my muscles are working hard. My body is going through a process called cellular respiration, which we'll chat about, to make energy. It's doing that a ton, and my internal body temperature will warm up, and I will sweat a lot. I will really sweat when I stop running and I come inside. Because if I'm outside, I've got that breeze, that wind, and it's always windy in Penticton, and that wind that I encounter outside speeds up evaporative cooling. So when it's windy out, your body's going to have an easier time cooling down because this phase change happens easier, and that helps pull more energy away. Maybe I'll even put that in brackets. This is easier with wind. The other thing I do to exercise if I've gone running too much and I've hurt myself is I will ride on my road bike on a wind trainer. So like my bike is like a stationary bike. And if I do a workout on my bike for 45 minutes or an hour and I don't have a fan blowing on me, I become just the biggest, sweatiest, most disgusting mess. And I'm cold before the ride, I'll be cold after the ride eventually, but I will just be sweating buckets while I'm sitting there on the bike. And that's because my body is working so hard to get this evaporative cooling happening, and without wind or a breeze on your skin, it's slower. So you really want to have it be, I guess, as windy as possible, just in terms of cooling things down. So evaporative cooling, and maybe I'll even throw that term in there, it prevents hyperthermia. It prevents you from getting too warm. So there are some videos you're going to watch about evaporative cooling. There's one, it's a TED Talk called Why Do We Sweat? There's another one talking about kangaroos. Kangaroos, like dogs, can't actually sweat. So you probably know that dogs can't sweat, so they pant instead, which is all about taking that moist mouth of theirs and their big long tongue and exposing that to the environment to try to get evaporative cooling happening. It's not as efficient as sweating for sure. If we were panting, I don't think we'd be able to run like we do or exercise like we do. It turns out kangaroos, there's actually a kangaroo on the wall to the left of the screen. There's a little sign that says, "What animal was this?" That's actually a kangaroo hide. Another story for another day. But I think I'm allowed to have it. Don't worry. The kangaroos can't sweat either, and they live in Australia where it gets really stinking hot. So in order to speed up evaporative cooling, they'll actually lick themselves a whole bunch. So they'll lick their arms, they'll get themselves nice and moist, and that way that water, when it evaporates off of their body, they don't have sweat glands to make the water show up there. So they lick themselves, put water on their skin, and then when it evaporates and changes to a gas, it pulls that energy away and cools them down. Also, the same reason why if it's really hot outside, sometimes people, before you go exercise, you might soak your hat in the water or soak your shirt in the water. And then you know that that's going to keep you cool, because as that wet clothing dries out, as it's evaporating, that water is pulling all that energy away from your body that your body's trying to get rid of anyway. So hopefully if you found that kind of fun, hopefully watching this video was not too onerous. Hopefully writing down a few notes was okay. Enjoy watching a couple videos on this material. If you have any questions about anything that we've chatted about, save those for me and ask when I'm back, or you could even fire me an email if you want a quick answer. I will check my email today. Enjoy the videos. I'm thinking watching this video and taking some notes, and then watching the 3 or 4 videos I've got lined up should probably take you to the break, where you can have sort of your 15 minutes to chill. And then we will reconvene with a second video looking at DNA and how DNA copies itself. But enjoy a couple entertaining videos, have a good break, and I will see, no, just kidding, you'll get to watch another video with me in a couple minutes. Thanks, guys.